Hi, in this video I will be talking about the reactions of conjugated dienes with just two reactions, but each one is a little bit complicated. The reaction with Br2 and the reaction with HBr. These are both reactions that you already know about when it comes to alkenes. You know that if you add two bromines to an alkene, the two bromines end up pointing on opposite sides, one up and one down, adding to the double bond to make it a single bond. And with HBr, you know that it adds one hydrogen on one carbon, one bromine on the other carbon, the double bond becomes a single bond, and that is a Markovnikov addition, so the hydrogen goes on the carbon that already has the most hydrogens. Well, what would happen if we were to take a conjugated diene and react it with Br2, let's say? Let's do a very simple case first. So if we looked at just plain butadiene, and we added excess bromine to it, excess Br2. That's easy. Each of the double bonds gets a pair of bromines. All the double bonds turn into single bonds. And you would get 1, 2, 3, 4 tetra bromo butane. And we are not going to worry too much about stereochemistry. It turns out that it's not stereospecific. You know that if you add bromine to an alkene, it's strictly anti-addition. You always get the trans product. Not true necessarily if you add it to a diene. And that's because the mechanism is not going to involve that 3-carbon bromine bridge with a positive charge on it, which is what steers the reaction to be an anti-stereochemistry with a single double bond. With two double bonds, you don't have that kind of a thing. We'll talk about the mechanism here in a minute. So then the question is, can you add just one equivalent of Br2 to a diene? And if so, what do you get? Well, let's try adding one equivalent of Br2. It turns out that you get what you might expect at first, and that is two bromines adding across this double bond, and the other double bond being unaffected. Again, though, you don't get necessarily anti-addition. In fact, it's non-specific, so you get both syn and anti. In this particular case, you can't really tell which one it was anyway because it's not a ring, and usually you can only tell the anti-stereochemistry on a ring, but it's not stereospecific. So you get 1,2-dibromo pentane, 1,2-dibromo butene, which is exactly what you would expect. However, you also get another product, and that is something a little unexpected. You would not necessarily predict this. You get the two bromines adding to opposite ends of the diene system. In other words, the 1, 2, 3, 4th carbon down, and the first and the fourth, and then the double bond that's left doesn't remain on the end. Instead, it moves into the middle position where there was no double bond to begin with. This is what we refer to as 1,2 addition. And 1,4 addition. Okay. Now, which of those is the major product? Which one would you expect? Well, there's two different answers, and I will let you think about it for just a minute and see which one you think would be the major product. Having had a chance, and hopefully you maybe turn off the video in between so that you can really think carefully about which one you would expect to be the major product. It turns out that there's actually two correct answers here. If you chose that as the major product, you are correct under some conditions. If you chose that as the major product, you are also correct, but under different conditions. Here's how you might argue it. This has a double bond that's more interior. In other words, this is a di-substituted alkene, and according to the Sate-Seth rule of formation of alkenes from non-alkenes, you would expect it to be the major product, simply because it's more stable. The more interior the double bond, the more stable the molecule. On the other hand, this one is only monosubstituted, so you might expect it to be less stable, so you might expect it not to be the major product. On the other hand, this is probably a quicker reaction in that once the first bromine adds here, it's really quick for the second one to add on here, as opposed to when the first one adds here, the second one has to go all the way down here, travel quite a distance to get down there. And so this might be formed faster. In fact, that is correct. this one is formed faster. You'll hear me say these phrases again and again, formed faster. And this one is more stable. Okay. This is what we call a kinetic argument. It has to do with the rate of reactions, and what we have to do is measure how fast the reactions happen, and if they happen faster, we might expect them to form the major product. On the other hand, we've always learned it in the past that if it's a more stable product, then that's the major product. Let me show you roughly how this works. This is what's known as kinetic. Kinetic meaning speed or rate of reaction versus thermodynamic control of a reaction. And generally what's going to happen in a situation where you have kinetics versus thermodynamics, in other words, if one product is formed faster but the other one is more stable, then you have this debate as to which one should be the major product. If you're starting with the same starting material, which we are in this case, just one particular starting material, it will have a certain amount of energy. We have two different products that we're forming, and they turn out to be both more stable than the starting material, so it's an overall downhill reaction, exothermic. This would be the product that's less stable, this would be the one that's more stable. So this would be the less stable, that's the 1,2 addition. And the more stable one is the 1,4 addition. Everybody follow what I'm saying there? If we just had a normal situation, the one that's more stable, that's lower in energy, would also have the lower hill that you have to go over to get to it. So the other hill would be higher and the product would also be higher. As it turns out in this situation, and in a fair number of other situations that we'll see in the future, the one that actually has the lower hill is the one that ends up being less stable. Notice there's a crossing over right there, so that the higher hill, the one that's slower to get over the hill, is the one that leads to ultimately the more stable product. So it's a higher mountain, but it's also a bigger valley. Smaller mountain, higher valley. So if whichever hill is the highest one is what controls the reaction, that's what's called kinetic control. And under kinetic control, this would be the major product because it only depends on which product is formed faster, in other words, which hill is lower. If, on the other hand, we don't care about the kinetics and all we care about is which product is more stable, that's what's called thermodynamic conditions, and then this would be the major product because it's more stable. So, what is the situation here, and what do we mean by kinetic conditions versus thermodynamic conditions? Well, think about this. If we gave this reaction lots and lots of energy, plenty of time, we allowed it to go back and forth, we really wouldn't care because all the molecules have plenty of energy to get over both hills. We really wouldn't care which hill was highest. It would pull up more down here than it does up there simply because that's lower in energy. So thermodynamic control is high temp, long time, essentially allowing the reaction to go to equilibrium, back and forth, so that we don't really care which product is the higher product. On the other hand, if we wanted to make the size of the hill important, and we really don't care what the products are, what we want to do is do it very quickly and give it not very much energy. So all the molecules would have just enough energy to creep over this hill and go down there and never have enough energy to go back again. So essentially kinetic control or kinetic conditions is low temp, short time, so we don't allow it to go into equilibrium. We barely give it enough energy to creep over the lowest hill and stop. Once it's crept over the lowest hill, it's done, so that's going to be the major product. Again, kinetic control, we do it for short periods of time under low temperature conditions. Thermodynamic control, we do it under high temperature conditions for a very long time, letting it go into equilibrium. Therefore, this one, which is formed faster, in other words, it's the kinetic product, would be the major product. If we keep it cool and short. This one, on the other hand, would be the major product if we heat it and do it for a long time. Okay? So, That's basically kinetic versus thermodynamic control, and this is the first situation we've run into in organic chemistry so far where it makes a difference what conditions you do the reaction under to predict which one is going to be the major product. Now I've got to say this is a massive oversimplification, but that's the basic idea of kinetic versus thermodynamic control. So let's do another example of this, only using a little bit more complicated starting material. And see if you can predict which one would be the major product under each of the different conditions that you may have. Okay, so what if we started with again a conjugated diene, but this time instead of 4 carbons we have 5 carbons. It's still double, single, double, and then we have an extra methyl group stuck on the end, so 5 carbons altogether. Can you predict which would be the major product if we had bromine, one equivalent to that reaction? Now what we're going to do is first predict what the two major products could be, and then we'll see which one would be formed under kinetic conditions and which one would be formed under thermodynamic conditions, if they are in fact different. In some cases they will end up to be the same product, or at least you get the same product under both sets of conditions. So what's the situation here? Well, now we have a more complicated situation than we did last time. And what we have to do first is think about the mechanism. We have to decide, will the first bromine add on this carbon, or will it add on this carbon? Because we know the first carbon is always going to add to the end, one of the two ends of the double bond system. Why would that be? Well, let's first look at if we add it to, let's look at each of the 4 possibilities. Is the first bromine going to go in there, 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 or there? So I'll just go ahead and put it on each of those. If we put it on this first carbon right here, there's the bromine, we end up with a positive charge on the carbon next door. Now please be aware that if that were the only double bond in the system, if this other one weren't here, that would be the 3-membered ring positive bromine molecule that we saw for regular alkenes. So why does it matter? Why is it not a 3-membered bromine bridge with a positive bromine in this situation? Notice that now our positive charge is allylic. In other words, it's next to another double bond, which means it's much more stable as a carbocation, which means this bromine doesn't have to get involved, and therefore it's just a regular allylic carbocation. And then, so we can draw another resonance structure for it, which we have to do if we want to take into account all the various possibilities. And the other resonance structure would involve putting the positive charge at that carbon down there. In other words, move the double bond over here and put the positive charge down there. So these are resonance structures that we would get if we added the first bromine on to the end carbon over here. What if we added the first bromine to this carbon right here? Well, notice that we'd end up with a positive charge over there. It would never have a chance to get that double bond involved, and so that's not going to happen. I won't draw the structure for that one just to save time, but you can think about it, you can draw it yourself if you want to. If we added the Br there, ended up with a positive charge at that carbon, that would just be a regular old primary carbocation. That would be very bad, and so that's not going to happen. It's not going to go on there. What about if we added the bromine on this carbon? Again, we'd end up with a positive charge over here, completely removed from the other double bond, no chance to draw any resonance structures, so it's not going to go there. But what if we put the double bond, what if we put the bromine on this carbon at this end? Let's look at that. So what we'll do is we'll have CH2, double bond CH, single bond CH. That double bond is going to become a single bond. We'll end up with the bromine on there, and then the CH3. Redraw that a little bit. Okay, and of course the positive charge there. Notice that the reason we can put the double bond either at this position, which is at one end of the diene system, or that position, which is the other end of the diene system, is that we end up in both cases with an allylic positive charge there next to a double bond, positive charge here next to a double bond. That means, of course, that we can draw another resonance structure for this. in which we moved the double bond from here into here and shifted the positive charge over to the other end. So these two are the resonant structures that you get if you add the first bromine on, let's call it position B. Let's call this position A, this is B. I've just made up my own notation system there. And just for consistency, I'm going to circle that positive charge and circle that positive charge. Now, looking at those two sets of resonance structures, is this a better set or is this a better set? Well, you might look at them and you might say, they're both allylic. This one has two resonance structures, that has two resonance structures, so therefore they should be the same. But if you look carefully, what kind of carbon is that? That's secondary. What kind of carbon is that? That's also secondary. So this resonance structure is sort of a hybrid between a secondary carbocation and another secondary carbocation. What about here? Well, that positive charge is secondary. That positive charge is, primary. So this is a hybrid between a primary and a secondary carbocation. So which is better, situation A or situation B? And the answer is situation A, because as we know, secondaries are more stable than primaries. So hybrid between two secondaries is going to be better than a hybrid between a primary and a secondary. Situation A is better. We can then forget about situation B. And we can predict that the first bromine then is going to go on there. Okay, having said that then, if the first bromine is going to go on there, where is the second bromine going to go? Well, it's either going to go 1, 2, or it's going to go 1, 4. So the two possible products, and I'm going to go ahead and erase this as well. We've now determined that situation A, where the bromine goes on there, is the best. But then we still have two possible products. If we put the bromine on that end, the first one, we can put the second bromine on right next to it, leave the double bond, the second double bond alone. So that would be the 1, 2 addition. Or we can, again, put the first bromine on that end, shift the double bond, put the second bromine on the fourth position, and since we have that extra methyl group there, we'll still have it there. So this is the 1, 2 addition, this is the 1, 4 addition. Of those two, which one is going to be the major product? Well, notice that we have the same situation we did last time, where this is going to be formed faster because the two bromines are right next to each other and it's easier to do it that way. But on the other hand, this one gives you a more stable product because the double bond is more interior than it is here. Or is it? Notice that this is a interior double bond, in other words, di-substituted. This is also an interior double bond, di-substituted. So two double bonds are the same strength as each other, same stability in essence. So that can't tell us in either case which one's going to be the major product. So in either case, the one that's formed faster is going to be the major product. In this particular case, simply because in essence, our energy diagram, we have a lower hill and we have a higher hill, but they both end up at the same place. So which one will be the major product? This one, under kinetic conditions, certainly the one that's formed faster will be the major product under kinetic conditions. What about under thermodynamic conditions? Plenty of energy, you can go back and forth, Which of these two products is going to be formed? Which is more stable? They're both the same, and therefore they'll be formed in 50-50 mixture. So here's the situation. 1, 2, under kinetic conditions, 50%, 1, 2, and 50%. Those are rough, not necessarily exactly 50%, but close to 50-50 under thermodynamic conditions. Okay, so here's the bottom line for bromination of a conjugated diene. You need to do two things. First thing you need to do is decide which end of the 1,4 system is going to get the first bromine going on, and that's just dependent upon which one gives you the more stable allylic carbocation. In other words, what's the hybrid between the two different resonance structures? Tertiaries better than secondaries better than primaries. So any combination of tertiaries over secondaries over primaries will be the one where the first bromine adds first. Then you have to decide what are the two possible products. If the first bromine adds here, is the second one going to add 1, 2, or is it going to add 1, 4? And the answer is both. And then you have to think about which product or products will be formed under thermodynamic conditions, in other words, which one's more stable, under kinetic conditions, which one's formed faster. And I will let you come up with your own examples. Basically draw any conjugated diene you might want, some in rings, some not necessarily in rings, and try it. And then we will do some examples in class. But we also have to think now about a little bit more complicated reaction, even than just plain old bromination. What makes bromination relatively simple, even though you can see it's obviously a little bit complicated, but what makes it relatively simple is the two things you're adding both are the same thing, two bromine atoms. What if we decide to add HBr? And this is just plain old HBr, no peroxides or anything like that. What if we add to a conjugated diene? And again, let's start with a simple one. And we're just going to add one equivalent. What are we going to get? Well, you have two possibilities. You can either add the hydrogen and the bromine next to each other on a double bond. In this case, it doesn't matter which one because they're the same as each other. That would be the 1,2 addition. And notice that I've done it with the hydrogen here and the bromine there rather than vice versa because it's Markovnikov. And the reason is because the first thing you do is the HBr protonates that carbon, leaves a positive charge there, which notice is next to a double bond, so it's allylic. Okay? That's way better than protonating here, which would give you the positive charge out of that carbon, unassociated with a double bond, no resonant structures, it's just a plain old primary carbocation. That would be bad. So the H plus is going to go there. Notice it could go at the other end just as well because it's the same in this particular case. That's the 1,2 addition. 1,2. But just like with Br2 addition to dienes, you can also get 1,4 addition. And again, those arise from the fact that once you protonate this, in fact, let's go ahead and draw it out. Once you protonate this in the mechanism, you get a positive charge at the second carbon, which is allylic, meaning it has another resonant structure in which you shift the double bond. And the positive charge moves to take its place. So these are the two resonant structures. After the first step in the mechanism, you protonate it and you get this allylic carbocation. The positive charge is here or here. And then in the second step, you're going to get the Br minus that's left over going on this carbon from this resonant structure, or this carbon from this resonant structure. Which one does it prefer to go on? Well, it depends on the conditions. If you're doing it under thermodynamic conditions, you'll get the more stable product, which would be this one, because the double bond's more interior. And so therefore that's the thermodynamic product. In other words, it's the one that will be the major product under thermodynamic conditions of relatively high heat and doing it for a long period of time. This one is formed faster because as soon as the HBr protonates this, the Br minus is right there, gets sucked right onto the positive charge. It doesn't have to travel all the way down to the other end of the molecule. And so that's faster. So this is formed faster, meaning it's the major product under kinetic conditions. Just exactly like we saw with the addition of Br2 to the diene system. Okay, let's do another example. This time I'm going to do one on a ring. Not that you have to use rings when you're doing HBr and non-rings when you're doing Br2. It's just we want to switch the situation up a little bit and do try both situations. So here is a conjugated diene. And just for fun, let's put a methyl group on here. Okay. So, first thing we have to decide if we're going to add HBr to this molecule, and I would literally do it in this way, and I would do it for the Br2 also. Before you even try to draw the products, go ahead and decide where's your first atom going to go. In the case of HBr, we're going to add an H+. In the case of Br2, it's as if you're adding a Br+. Okay? So where's the H+ going to go? Is it going to go on that carbon, which is one end of the diene system, or is it going to go on that carbon, which is the other end of the diene system, or is it going to go somewhere in the middle? They never go in the middle. The first atom that adds will always add to one end or the other of the diene system. That's what we learned a few minutes ago when we did the Br2 case. But you still have two different ends in this case, because of that darn methyl group there, you have two different possibilities. So should we protonate here? And if so, the carbocation that we would end up with would have the positive charge there, which is then in resonance with that carbocation. Notice I just moved the double bond from there to there and moved the positive charge down there. So there's the two resonance structures you would get from protonating at that position. Let's call that A, just for to keep track of things. So that's situation A. The other possibility would be to protonate at that carbon. Let's call that situation B. If we protonate there, the first carbocation we would get, that double bond wouldn't be affected. We protonate there, so we get the positive charge at that position. And of course it has a resonance structure in which we shift the double bond there, move the positive charge up to there. Okay, so from this from this carbocation to this carbocation, I moved the double bond down there and shifted the positive charge up there. And again, just like we've been doing all along, since all these things are allylic, there's always going to be two resonance structures for them. Now, and that's situation B, isn't it, if we protonated at that carbon. Now, looking at those two sets, is this a better set of resonance structures, or is this a better set of resonance structures? And the answer is this one is a hybrid between a tertiary and a secondary carbocation. This is a hybrid between a secondary and another secondary carbocation. So clearly situation A in this case is better. Okay, you just have to look at all the possible resonance structures and decide which is a better set of resonance structures based on primary, secondary, tertiary. And by the way, if you come up with the same answer in both sets, then they both form, and they'll be formed in about equal amounts. In this case, we can say that A is a better set, therefore we will protonate at that position, and we can just pretty much eliminate this set right here. Now, given that, then the next thing we're going to do is add the Br minus, and the question is, will the Br minus end up here? On the same carbon with the CH3, because there's a positive charge at that position and a double bond there. Or will we end up with the Br adding at that position, double bond there, CH3 there. In other words, this resonance structure would give us this product, that resonance structure would give us that product. But notice, as was true in the other situations we've done, the products are not resonance structures. This one arises from this resonance structure, this one arises from that resonance structure, but these are not resonance structures. They're actually different products, and so you have to decide, would you get more of this product, or would you get more of that product? What do you think? I'll let you think about that for just a minute. Okay, well, if you're following the argument, which one of these two products is going to be the more stable product? Well, that's this one, because in this one the double bond has 3 other carbons attached to it. We call it tri-substituted, and that, according to the Zaitsev rule, is the more stable product. And then the one that's formed faster is the one where the hydrogen and the bromine both added on the same carbon. Well, we added the hydrogen on this carbon, not on the same carbon, but on carbons next door to each other. In this particular case, we added the hydrogen there, the bromine goes there, so that would be 1, 2. That's quicker, in other words, formed faster. Whereas in this one we added the hydrogen over here and the bromine all the way on the other side. So the bromine had to travel around the ring to get to here in order to attach to the fourth position. So this is faster, that's more stable. This is the kinetically formed product. It will be formed if you do the reaction quickly and under relatively cool conditions. This is the thermodynamic product. It's the one that will be formed if you give it plenty of heat and plenty of time. That's the product that you're more likely to get. Any questions? Thanks for your attention. We'll see you later.